Hi all! This episode of Physical Attraction is brought to you by the American National Standards Institute. Standards make the world go round, and they also dictate what is round. Without standardised measurements and definitions, physicists would be speaking to each other in different languages and would struggle to understand the universe even more than we already do. You can learn about standards in America at the ANSI blog at blog.ansi.org/pod to learn about how standards apply to you. Now on with the show.
Into his eyes. They're the eyes of a man obsessed by sex. Eyes that mock our sacred institutions. Bedroom eyes, they called them in a bygone day.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time.
But for corrupting others to a life of carnal pleasures and lewd designs. A man whose erotic desires and libertine practices are used to titillate the unsuspecting and would stoop to any depth.
Hello, and welcome to Physical Attraction. This is the second part in our series of episodes on units and dimensional analysis. In this episode, I'm going to be talking about dimensional analysis, which is something that sounds incredibly complicated, but is in fact very, very simple. Last episode we talked about how we came by the SI system of units, from the French Revolution through to the more modern definitions that don't rely on blocks of platinum for length anymore. The units we've been stuck with then are a little strange. But really, it's not just the candela that depends on humans for a real definition. A metre makes sense as a unit of distance for the human. It's comparable to human scales. Stretch out your arms, it's about a metre. Your height, it's about a metre. It's certainly not 10 metres or 10 centimetres. Similarly, kilograms are sort of defined on human scales for mass as well. A kilogram is approximately the weight of something you can hold in your hands. But if you compare this to the fundamental building blocks of the universe, the most common things, grams and kilograms are pretty arbitrary. Stars are closer to 10 to the 30 kilograms. Subatomic particles are closer to 10 to the minus 30 kilograms. In the range of things we can conceive of in physics that exist in the world, we can go across tens of orders of magnitude. It's only in this intermediate range, the human domain, the domain of plants and people and things, that we define our terms and set our yardsticks. There are proposals that will be enacted in a couple of years to change the definitions of some of these quantities to be more like the metre. The metre is now defined in terms of a fundamental physical constant. It's defined in terms of the speed of light and a time. One of the numbers, the rules, the laws, if you like, that's hard-coded into the universe, as far as we can tell. The speed of light in a vacuum is the same everywhere, and we define a metre as some fraction of that speed of light. That speed has an exact value, and if we get any better at measuring it, this is what changes the length of a metre. So in a sense, the length of a metre is now something that we don't define by the length of a specific block. It's something that's defined by the speed of light, and we're learning more about how long a metre is as we measure the speed of light to ever greater degrees of accuracy. Doing things this way makes everything a little more neat and tidy, and so it's been proposed to determine other SI units as multiples of fundamental physical constants, or combinations of them. Basically, this will mean that the kilogram lump of metal will become obsolete. As early as 2018, so possibly already when you hear this, that kilogram lump will be consigned to the dustbin of history. Although not an actual dustbin because it's 90% platinum. I guess they'll probably use the metal for something. And it will be replaced by some fraction of Planck's constant and the speed of light and so on. And thus another link between the old world and the brave new one will be severed. But instead, the ways that we describe the world will be linked more intimately to the laws of physics. And presumably, the heavily armed SWAT team that guard the kilogram and defend it with their lives can stand down and take up flower arranging instead. At this stage, you're probably thinking, it seems like people have spent far too long thinking about incredibly precise definitions for all of these units. In some ways, that's correct, but if you've ever spent ages getting your maths wrong because you faffed around with too many conversion factors, you'd understand completely. There's a reason we don't use miles and so on. You'd have to come up with a very consistent definition for these new units. You'd have to derive new units for force and so on. And you'd have to deal with a whole bunch of unpleasant conversion factors. 1 Newton acting for 1 metre gives you 1 joule, and you can carry around fewer numbers, which you invariably forget and which mess up your calculation, leaving you scratching your head for hours, trying to catch where you went wrong. But units, or this concept of dimensionality, It's important for another reason. A method so simple and elegant and yet with such amazing results in physics that it almost does live up to this incredibly cool sounding name. I'm talking, of course, about dimensional analysis. Dimensional analysis is really just a super fancy name for checking that your units match. If I tell you that I add one apple to one banana and end up with 2 oranges, you'll probably be sceptical that my fruit recognition license is really as legit as I claimed it was. But the reason you know that's obviously wrong is dimensional analysis. You know that the units don't match. You can't add an apple to a banana and get a couple of oranges. Similarly, in physics, imagine you've come to the end of some incredibly long calculation. Maybe you're trying to derive the amount of time it will take for you to get over Firefly being cancelled. But you realise straight away that it will depend on all kinds of different factors. How many new shows are getting produced a year? How good are the shows? How quickly does your emotional intensity decay over time? That kind of thing. So you throw it all into a super complicated equation, you solve that, and you get a formula for t that depends on all the parameters you threw in. But it's late, and you had to work across 17 pages of algebra, and maybe, eyes filling with tears as you realise that Joss Whedon is moving on, so why can't I? You don't know if the formula is correct. One test is to see if the units of that formula are actually in terms of time at all. If they're not, if they're in units of sadness instead, then you've made a mistake somewhere. And this gives you an invaluable chance to check your work for consistency, and more than once I've had to throw out an answer for giving times instead of masses, or similar things like that. But the power of dimensional analysis is far greater than just allowing you to check that you've done your algebra correctly. If used correctly, it has some incredible predictive powers about nature and science. In 1950, just a few years after the first nuclear explosion had occurred at the Trinity test in Los Alamos, a mathematician called G.I. Taylor published a fairly unusual mathematical paper. It was unusual because it contained a piece of highly classified information that hadn't been leaked to the public: the yield or explosive force of that first nuclear test. This had been kept secret by the US military and had been considered to be a very secretive, sensitive piece of information. How had Taylor got his hands on it? The answer was dimensional analysis. Although the yield of the bomb had been kept secret, photos and video of the mushroom cloud had been published in 1947 to a fascinated and rather terrified audience. They watched it and saw what Oppenheimer saw that we discussed in our Teot Wauke specials, the slowly dawning realisation, as the cloud slowly spread, that humans had unlocked incredible, almost unearthly power, and that it would change the course of human history from then on. But G.I. Taylor saw something else. He realised that he could use this to estimate the yield of the nuclear bomb. And you can do it more or less with a simple case of a little intuition and some dimensional analysis. So imagine ourselves in the future. We've got a nice neat formula that links together the energy of the initial blast with information about the fireball that he could figure out by looking at these videos and these pictures. What might be in that formula? Well, the fireball is expanding, so we better include its radius, r, a measurement of its length. Since it's expanding, time t since the explosion is also going to be important. The energy of the bomb's explosion, which is what we're trying to find out, is the yield, and you can imagine that it will determine how quickly the fireball expands, right? So we should chuck that in as well. And finally, the density of air surrounding the bomb. This is slightly less obvious than the others until you think, okay, well what if we exploded the bomb in incredibly dense treacle rather than air? Clearly this impacts how quickly the shockwave and the fireball can spread. So we've identified the physical parameters relevant to the problem of the expanding fireball. We've got the energy, the time, the radius, and the density of the surrounding air. We know that there's probably also going to be some dimensionless constant of proportionality involved. This is really something of a guess, but things really scale with each other perfectly. For example, the volume of a sphere scales with the cube of the radius, but it's not equal to the cube of the radius. It's 4/3 pi times the cube of the radius. That kind of thing. So this constant might even turn out to be 1, but you need to throw it in there. And then we can actually use dimensional analysis to work out how the quantities all relate to each other. Let's say that the formula we're looking for lets us write the radius of the bomb blast in terms of the constant, time, the energy, and the density. We know that if this is true, the dimensions have to match. So we can ask ourselves, how can you multiply together a time, an energy, and a density to give you a radius. How can you get those units to match? And it turns out that here we're just dealing with the 3 SI base units of length, time, and mass. And it turns out that you can do the maths yourself. There's only one way to do this so that the units match. The formula must be true. R to the power of 5 is equal to a constant times energy times the time squared divided by the density. So this is pretty incredible, because you can plot the radius to the power of 5 against time squared, and the gradient of that is some constant times the energy of the bomb divided by the density of the surrounding medium. Plug in the density of the air, and you have some constant times the highly classified energy of the bomb. Whenever you come up with a formula in physics, the best thing to do is to sanity check it. That means you think, okay, what do I expect to happen based on my knowledge of the laws of physics and common sense in general? So, just as an exercise, let's do that for this formula. R to the 5 equals ET squared divided by rho. Now we can see straight away that the radius increases as time increases, because R to the 5 is proportional to t squared. And that's good because we want our fireball to grow when our bomb explodes. Obviously it's no good if you're about to be eaten up by the fireball, but let's not worry about that. We can also see that the rate of growth depends on 2 things: the energy and the density of the surrounding air. It would be the gradient of that graph of R to the 5 against t squared. If the energy of the blast is bigger, the fireball grows more quickly. And that makes sense, right? A bigger boom, you'd expect the fireball to grow quicker. If the density of the surroundings is higher, then the bomb blast grows more slowly. Okay, that also makes sense. Shockwaves might spread less quickly through treacle than air. Does this mean that the formula is necessarily correct? No, it doesn't mean it's correct, of course, but it doesn't mean that it's obviously wrong. It fits well with our common sense. Similarly, if you discovered that your Firefly happiness formula predicted that you get sadder over time rather than recovering, you'd need to explain it. All that's left is the constant. Working out that constant was the really clever bit for Taylor. It turns out to be very close to 1, and you can work it out by considering how shockwaves that aren't due to nuclear blasts behave. So he generated some shockwaves in the lab, probably in liquids, and he managed to, with fairly simple maths, derive a value for the classified explosive energy of that first nuclear bomb. He figured out the constant, which was dimensionally similar, and he worked out the energy of the yield. Now you can formalise this method of dimensional analysis to figure stuff out using something called Buckingham Pi Theorem, which is an incredibly useful result. What it does is it tells you how to construct dimensionless quantities from the parameters of interest that do have dimensions. You can then use that to construct these simple rules about how your physical system will behave. And amazingly often, when you go through and solve the actual calculation, you find out that the dimensional analysis estimate was pretty good. And this is really important for a couple of reasons. First off, you don't need to know all that much for dimensional analysis. You just need to know which parameters of the system you're interested in. You don't need to know the underlying equations that govern the physics. So, we've worked out, in this case, how the radius of the bomb blast expands with time without knowing anything about fluid mechanics, without knowing anything about explosions, without really knowing anything all that much about how the air molecules are being pushed around by the shockwave. We don't need any of that mathematics to get this simple scaling relation. And similarly, you could use dimensional analysis to calculate, for example, fluid flow in a pipe. And you wouldn't have to solve the Navier-Stokes equations, the equations that tell you how fluids behave and are often notoriously difficult to solve. There are whole careers that are just based around finding new ways of solving numerically the Navier-Stokes equations. That's what you'll do, for example, if you're one of the engineers working on new designs of Formula 1 car. But in this case, if you want to solve it for a simple situation with a simple scaling law, you wouldn't even need to know that that equation exists. And sometimes we don't know what the underlying equations are for our physics, so dimensional analysis is sometimes as good as we can do. What's more, if you're running an experiment, it can tell you about how what you're trying to measure might depend on other parameters in the system. And this is so important because the best way to get the right answer is often to have some idea of the answer that you're trying to get to in the first place. In other words, if you can use dimensional analysis, the last refuge of the scoundrel, to find a formula that looks good and makes physical sense when you sanity check it, and it agrees with the evidence and measurements, You can save yourself a whole lot of work trying to work out the underlying equations and solving them, and you have a guideline when you're trying to solve those equations for what you're looking for. You can even get super profound results directly from dimensional analysis if you're smart to begin with. Let's say that I have one of the physicist's favourite problems, a block attached to a spring. You move the mass a little bit and it starts to oscillate, bouncing up and down. Is there a way to calculate the time period, how long it takes for a full cycle of oscillations, so that the mass returns to where it was? Well, there's a similar story here. What does it depend on? We're just estimating, so let's ignore friction and air resistance. You might expect the mass of the block to matter, and the stiffness of the spring too. You might also initially think that the gravitational field is important. After all, surely if the weight of the mass on the spring is bigger, that has an impact. But when you go through and do the dimensional analysis, you find that there's no way to sensibly get time out of the spring constant, which tells you how much force you need to extend the spring, gravity, and the mass. You know that the spring constant is important because you've tested a couple of different springs, and you realise that the time period of oscillation depends massively on the spring. So you assume then that you can discard the gravity. The reason for this turns out to be that the mass is important because it determines how strong the spring has to be to snap back the block in a certain amount of time. Basically, the weight of the block, including gravity, just determines the equilibrium position of the spring. The mass is only important because it tells you how the spring forces can accelerate the block. And it turns out that the dimensionless combination gives t equals constant times square root of m divided by k. So let's do a sanity check. A stronger spring takes less time to oscillate. It has a shorter time period. Okay, well that makes sense because the spring is stronger and it's responding with a bigger force. If the mass is bigger, the oscillations take longer because t, the time period, is proportional to the square root of m, the mass. And that makes sense too, because if the mass is bigger, there's more inertia in the system. It's harder to change the motion of the mass. This is exactly what you get from Newton's second law and solving the differential equation for the spring block motion, but we didn't need to use Newton's second law. We didn't even need to know Newton's second law, and we certainly didn't need to solve any differential equations. We just needed to use units and a little bit of logic. Obviously the magic part of this is knowing precisely what quantities your final answer depends on. Dimensional analysis can help you with this, but it can't rule out that you're actually getting the correct answer every time. So you do need some physical understanding of the processes that are going on. You need some prior expectations, and you need, ideally, some way of testing them. But this process is incredibly valuable in physics, both for sanity checking your answers, and for estimating how quantities might increase with each other, to get simple formulae to solve and estimate the problems. Often, a more careful analysis leads to very similar results from the quick, back-of-the-envelope dimensional analysis. And in things like fluid mechanics, it can become even more useful, where you can derive dimensionless parameters that determine how your system will behave. One example is the Reynolds number, and another example is the Mach number, which you probably know they use for aircraft. It's multiples of the speed of sound. But that will have to be for another day. I hope I've given you some insight in the last couple of episodes into the incredibly geeky but very important people who keep track of our units, and how you can learn to stop worrying and dimensionally analyse the bomb. Next time someone tells you that you can't compare apples and oranges, you can tell them that you worked it out with the mathematical method of dimensional analysis. And then you can watch their head explode. And then you can work out how the radius of that explosion depends on time. It's that useful. I'm going to finish with some non-SI units that have been defined over the years. So scientists are often very nerdy, many of us love terrible jokes, and many of us have a weird obsession with units. So it seems a little appropriate to end this way. So those of you who follow American politics will know that Anthony Scaramucci briefly served as the White House Director of Communications, at least until he was fired for giving an obscene and probably drug-addled interview with a magazine. Remember that? Well, his tenure was so short that he defined a new unit of political time. The Scaramucci is 11 days long. Similarly, from a little while before that, people got so sick of the columnist Thomas Friedman saying that the next 6 months will be crucial in determining the fate of the Iraq War, that they defined 6 months as one Friedman. Sometimes these funny units are useful. In some cases we have units, but people don't understand what they mean. What if I told you, for example, that you'd just been exposed to a microsievert of radiation? Should you be worried, or is this fine? Well, bananas are naturally slightly radioactive. They're high in potassium, so every time you eat one, it's slightly radioactive, because there is a radioactive isotope of potassium. But this probably doesn't bother you too much. You're probably not concerned, in your chief list of concerns, about the radioactive dose from eating bananas. So when I say that 1 microsievert is 10 banana equivalent doses, or BEDs, you probably wouldn't feel too nervous. The average dose of radiation from people around the 3 Mile Island accident was 80 microsieverts. It might worry you to put it like that. If someone came to your house and said, "You know that nuclear plant that just blew up near you, you've been dosed with 80 microsieverts." But if you say 800 bananas, it doesn't sound nearly so bad. It takes 4 to 5 sieverts to kill a person. Similarly, micromorts measure the risk from day-to-day activities. A micromort is equivalent to a 1 in a million chance of dying, so driving 370 kilometers in your car boosts your death risk by a micromort. Scuba diving is 5 micromorts. Douglas Adams, the late great author of The Hitchhiker's Guide to the Galaxy, defined the sheppy as 7/8 of a mile. He said it was, quote, the closest distance at which sheep remain picturesque. And yeah, if you ever got up close to a sheep, you'll get what he means. If anyone can define a unit of the closest distance at which I remain attractive, please send your answers on a postcard. Andy Warhol famously said that in the future everyone will be famous for 15 minutes. So by now, you've probably been listening to this episode for almost 2 Warhols. A unit of distance that people like when they talk about space and astrophysics is the light year. It's a phenomenally huge distance that is simply how far light travels in a single year. The nearest star to Earth is about 4 light years away, aside from the Sun. But you can get a much smaller unit by considering how much facial hair grows, a unit of distance called the beard second. Apparently it's around 5 nanometers, so an atom is about 0.2 beard seconds across. And as you might think, yes, of course, the beard second is how long the average beard grows in 1 second. Because Carl Sagan, the famous astronomer and science communicator, had a catchphrase, billions and billions, which is often useful when you're talking about outer space in terms of human-sized units, a Sagan is a large quantity of anything. Similarly, the physicist Paul Dirac, who made immense contributions to theoretical physics and quantum mechanics, was also famously very quiet and seldom spoke. In some ways, he's portrayed by history as this archetype of the quiet, reserved but immensely intelligent physicist. He was so reluctant to indulge in idle chatter that his friends defined a unit of information flow, the Dirac. It's 1 word per hour. When I was an undergrad, I used to turn in incredibly lengthy problem sheets. To give you a sense of perspective, you'd usually get 1 to 2 problem sheets a week. The longest one I ever turned in was over 100 pages of A4. So yeah, I was wasting a lot of time. Other people define their Hornigold factor, which was the number of times longer my problem set was than theirs. I guess it measures conciseness, since they always got the same marks as me, and it just took me 3 times as long to get them. I could certainly define an empirical law that says that the number of shows that it actually takes to cover a topic is between 2 and 3 times the number that I think it will take. I've thought of another one. How about a personal unit of time that measures how long, on average, you can go without checking your phone or social media? We can call them distractions. Can you guys come up with any more humorous or useful units? I'll read out good suggestions in a future episode. You can submit them all via www.physicspodcast.com or by following us on Twitter @physicspod. Anyway, I hope this nerdy foray into physical units and dimensional analysis has been fun. Until next length divided by speed. Thanks for listening.